Today we are going to learn about fine-tuning techniques for large language models. We will explore practical strategies for fine-tuning LLMs to adapt pre-trained models to specific tasks or domains efficiently, enhancing their performance.
Fine-tuning large language models is a crucial step in adapting these pre-trained models to specific tasks or domains. By the end of this video, you will have practical strategies to enhance model performance through effective fine-tuning. We'll discuss selecting appropriate datasets, adjusting hyperparameters, using transfer learning, incorporating domain-specific vocabulary, balancing model bias and variance, evaluating model performance post-fine-tuning, utilizing transfer learning frameworks, and integrating feedback loops for continuous improvement. Let's dive into these concepts and equip you with the skills needed for successful fine-tuning. The first step in fine-tuning large language models is selecting the appropriate datasets. Quality data is the backbone of model performance. Start by identifying data that aligns closely with your specific task. This means ensuring the data is relevant and representative of the domain you are targeting. For instance, if you're fine-tuning a model for medical applications, using datasets containing medical terminologies and case studies would be beneficial. Next, consider the size and diversity of your dataset, as larger and more diverse datasets can help the model generalize better. However, it's crucial to balance this with domain specificity to avoid diluting the focus. Additionally, always evaluate the potential impacts of your dataset choices on model performance. Assessing the quality and relevance of your data throughout the fine-tuning process will ensure you're on track to enhancing your model's performance effectively. Hyperparameter tuning is a pivotal aspect of fine-tuning language models. Key hyperparameters such as learning rate, batch size, and epochs need careful consideration. The learning rate determines how quickly the model updates its parameters. A rate too high can lead to overfitting, while too low might slow down the training. Batch size impacts the stability of the optimization process, with larger sizes providing stability but requiring more memory. Similarly, deciding on the number of epochs involves balancing training time with performance gains. Dropout rates, which help prevent overfitting, must also be fine-tuned based on the complexity of your task. Each of these hyperparameters can significantly impact model accuracy and efficiency. By systematically adjusting and validating these parameters, you can tailor the model to perform optimally for your specific application. Transfer learning is a powerful technique that leverages pre-trained models to improve efficiency in fine-tuning tasks. By using models pre-trained on large and diverse datasets, you can significantly reduce the time and resources needed for training. This is especially beneficial when dealing with tasks where data is limited or expensive to obtain. The advantage of transfer learning lies in its ability to utilize the knowledge acquired from previous tasks to enhance performance on new, but related tasks. For example, a model trained on general language data can be fine-tuned for specific domains like legal or scientific texts with less data and time than training from scratch. Real-world case studies show how companies have successfully implemented transfer learning, reducing training costs and improving model accuracy. By incorporating transfer learning, you can streamline your fine-tuning process, making it more efficient and effective.
Incorporating domain-specific vocabulary is crucial for adapting large language models to specialized tasks. This involves enhancing the model's understanding of unique terminologies and jargon that are pertinent to a particular field. For example, in the financial sector, terms like derivatives and annuities must be well understood by the model to provide accurate outputs. Adapting pre-trained models to include such vocabulary can significantly improve their comprehension and accuracy in the domain of interest. Tools and techniques such as tokenizers can be used to integrate new vocabulary seamlessly. Moreover, creating custom vocabularies that align with the pre-trained model's architecture optimizes comprehension. This adaptation not only improves the model's ability to generate more contextually relevant responses but also ensures a higher level of accuracy in task-specific applications.
Balancing model bias and variance is essential in fine-tuning large language models. Bias refers to errors due to overly simplistic assumptions, while variance involves errors from excessive complexity. A high bias model may underfit, missing critical patterns, whereas a high variance model may overfit, capturing noise as if it were a pattern. The goal is to find an optimal balance that allows the model to generalize well to new, unseen data. Techniques such as cross-validation, regularization, and using validation datasets can aid in achieving this balance. Regularly evaluating model performance on diverse datasets helps ensure that the model adapts appropriately without succumbing to either extreme. By understanding and addressing the trade-offs between bias and variance, you can develop a more robust model that performs effectively across various scenarios.
Once fine-tuning is complete, evaluating model performance is crucial. Metrics such as accuracy, precision, recall, and F1 score provide insights into model effectiveness. The use of validation datasets is vital for unbiased evaluation. They help in understanding how well the model generalizes to new data. Continuous performance monitoring is important as it allows you to identify areas needing improvement and adjust strategies accordingly. This might involve retuning hyperparameters or refining datasets. Real-world implications of these evaluations cannot be overstated, as they directly impact the reliability and applicability of the model in practical scenarios. Regular evaluations ensure that the model remains aligned with the goals and requirements of the specific task, enabling it to deliver optimal results.
Leveraging transfer learning frameworks can greatly facilitate the fine-tuning process of large language models. Popular frameworks like TensorFlow Hub, PyTorch Hub, and Hugging Faces Transformers offer comprehensive tools and resources. These frameworks simplify the implementation of transfer learning, providing pre-built models and easy integration capabilities. They support a wide range of tasks, from language translation to sentiment analysis, making them versatile and powerful. The active community and abundance of resources available for these frameworks further enhance their utility, offering support and insights for troubleshooting and optimization. When selecting a framework, consider factors such as ease of use, compatibility with your existing systems, and the specific requirements of your task. By choosing the right framework, you can streamline your fine-tuning process, making it more efficient and effective. Integrating feedback loops into your fine-tuning strategy is essential for continuous model improvement. Feedback loops involve using real-time data and user feedback to refine model performance continuously. This iterative process not only enhances model accuracy over time but also adapts it to changing environments and user needs. By incorporating real-time data, models can learn and adjust dynamically, ensuring relevance and efficiency. Iterative improvement processes enable constant refinement of the model, addressing any emerging issues promptly. This approach is vital for maintaining high performance in the long term, providing a robust solution that evolves alongside user requirements and technological advancements. Through effective feedback integration, you can ensure your model remains competitive and aligned with its intended purpose.
In conclusion, fine-tuning large language models is a dynamic process that involves selecting appropriate datasets, adjusting hyperparameters, leveraging transfer learning, and incorporating domain-specific vocabulary. Balancing model bias and variance, evaluating performance, utilizing frameworks, and integrating feedback loops are crucial steps for optimizing model performance. As the field of language models continues to evolve, staying informed and continuously learning are vital. These techniques not only enhance current capabilities but also prepare you for future advancements. We encourage you to apply these strategies in your projects and explore further to fully harness the power of large language models in your domain.